Today is a continuation of our lecture for thin-walled pressure vessels. In the previous meeting, we discussed how to derive these equations. First, for bursting force, F equals PdL. This is the force experienced by the sides of your cylinder. Next, FL, your longitudinal bursting force, pi of P times pi d squared over 4. This is the force being experienced by the ends of your cylinder. Next, your tangential stress, also known as your circumferential stress. Sigma T for tangential equals PD over 2T. This is the stress experienced along the circumference of your cylinder. And then last, your longitudinal stress, it's sigma L for longitudinal equals PD over 4T, and that is along the length of your cylinder. We also found out that sigma T, or tangential stress, is critical or more critical. Therefore, this is the equation or stress that we'll use whenever we're looking for dimensions or force, maximum force, and the like. Okay, so to better understand these equations, let's have a few examples. Number one. Okay, now for number one, as I've mentioned before, I'm gonna answer this on my own. Okay, you can just listen. I'm not gonna take any recitation yet. So you can still try to solve for it on your own, but again, I'm not taking recitation. Number one, a cylindrical steel pressure vessel 400 millimeters in diameter with a wall thickness of 20 millimeters is subjected to an internal pressure of 4.5 meganewton per meter squared. Calculate the tangential and longitudinal stresses in the steel. And then letter B, to what value may the internal pressure be increased if the stress in the steel is limited to 120 meganewton per meter squared? Okay. Once again, we derive this. Next. Let's answer. Okay. So first step, usually for problems like this, is to write the given. So first, cylindrical steel pressure vessel 400 millimeters in diameter. So D, 400 millimeters with a thickness of 20 mm. So that's your T. Subjected to internal pressure 4.5 meganewton per meter squared. And that is also equal to 4.5 MPa. So that's for part A. Then we have a follow-up question for part B. To what value may the internal pressure be increased if the stress in the steel is limited to 120 meganewton per meter squared? So limited to 120, that means that's the maximum stress that your system is allowed to experience. So that's your sigma max, 120 meganewton. Okay, so sigma max 120 MPa. Okay, let's start with letter A. Once again, we're looking for tangential and longitudinal stress. So that's easy. We just need to direct sub our equation. So tangential, that's PD over 2T, right? PD over 2T. Let's check. Yep. PD over 2T for tangential. Sub in your values. Our P is 4.5 MPa. So 4.5. Our unit, this is also equal to Newton per millimeter squared. And our dimensions are in millimeter, so no problem there. You can still, no need to convert. So 4.5 times D, which is 400, over 2 times thickness, 20. Solving for this, you should get 45 MPa. Yes, correct. 45. Then stress, same with your pressure. This is Newton and millimeter, so MPa. Okay. Now, to get longitudinal stress, you can just divide this by 2. You're going to get the longitudinal stress, or if you want, you can go through the equation PD over 40. So that's 4.5 times 400 over 4 times thickness 20. You're going to get 22.5 MPa. Yes, correct. Okay, so that's part A. Now for part B, it's different. To what value may the internal pressure be increased with your limit for the stress? So now the question is, what can be the maximum pressure our vessel can experience, considering this is the maximum stress? Now for this, we're looking for maximum force. So you need to check which would yield the lesser force between your situations. Okay. For example, in our previous lecture, right, we solved for two forces, right? One for bearing stress, one for shearing stress, and whichever yields the least amount of force between the two, that is the allowable force. Okay. That is because we don't know which of the two is the critical force. It depends on the dimensions and properties of your material. However, for thin-walled pressure vessels, okay, tangential stress will always create a lesser force or a lesser allowable force than longitudinal stress. That's why we call it critical, because under the same force, okay, same force, tangential stress, as you can see, is always greater than longitudinal stress. Therefore, this experiences greater stress. This is the more important stress to consider. Right? So use the critical stress, meaning the stress that's most likely to cause your system to fail. So again, that's tangential stress. So the equation is sigma T PD over 2T. Now, sigma T, that's the maximum stress that is allowed, and that's equal to 120. By the way, sigma T and sigma L are only different in terms of their placement. Sigma T is just along the sides, or rather along the circumference. Sigma L is along the length. Okay, so that's why they can both have this maximum 120 MPa. Okay, so 120 MPa equals P, which is what we're looking for. Diameter is the same, that's 400 over 2 times thickness 20. Okay, solving for P, the maximum pressure that we can get is 12 MPa. Okay, that's number 1. Correct? Any questions for number 1? Please answer in the chat. Okay, great. So number 1 is pretty easy so far since it's just direct sub. Okay, so our questions will progressively get harder. So now number 2, okay, I'm gonna take recitation now, ready your calculators. Number 2, the wall thickness of a 4 feet diameter spherical tank is 5/16 of an inch. Calculate the allowable internal pressure if the stress is limited to 8,000 psi. So again, we're looking for pressure given maximum stress. So first step, write out your given. Wall thickness 4 feet of a 4 feet diameter spherical tank. So the diameter of your spherical tank is 4 feet. So write that out. Diameter 4 feet. And then the thickness is also given of your spherical tank to be 5/16 of an inch. So as you can see, we already have an inconsistency in unit. So we need to convert one of them. And then next, calculate the allowable internal pressure, looking for P. Stress is limited to 8,000 psi. So sigma max, sigma allowable, 8,000 psi. And again, psi is just pounds per square inch. Okay, so that's an easy way to solve for this if you already remember what I said in the previous meeting. But in case you don't remember, I'm going to show you how to solve for it by deriving. Oh. So that you have an idea for a spherical tank. Okay. Then so we have this spherical tank. So what's gonna happen here? Remember again, the goal is to get maximum pressure allowed given maximum stress that this spherical tank can experience. Okay? So to derive, recall, we have force because of the pressure being experienced by the tank. Okay? So this is your force from the pressure inside the tank. And then this force will be repelled or gonna create a reaction on the actual vessel itself. Okay? So this is gonna react. Okay? Gonna be reactions here for this force. Okay, to negate that force. Yeah. Okay, and then because of this force and these reactions, that reaction creates stress in your material. So that's your stress. Okay, there's stress within the material. Okay. And this force will actually be repelled by the combination of the forces along this circumference here. Okay, let's call this T, right? Because this is a tangential force. So that's your free body diagram of what's happening in a spherical tank. Again, there's going to be a force because of the pressure applied in your cylindrical, your spherical vessel. Okay, because of that force, your tank will experience stress along its material. Okay, and that stress creates a resisting force T to your force F. So that's your free body diagram. Okay, then we can use our equilibrium equations to create an equation out of it. So let's say summation of forces equals 0 because there should be an equilibrium. Your spherical tank is not moving. So therefore, okay, if we take forces y equals 0, we'll have T, positive T minus F equals 0. Since P is upward, F is downward. And then you'll see P equals F. And then recall P is created from the stress experienced by this tank. And recall stress is equal to P over A. Okay, so P is sigma A. So P is equal to sigma A, right? And that sigma is along this material, along this area. Okay, so therefore, this is the area that we're concerned with. Okay, that's the one experiencing the stress. So can anybody give me the equation for that area? Okay, and then this is actually, again, I'm looking for area. What is the equation for the area of this portion? Correct, Cecilia. It's pi dt. Why? Pi. Pi d is the equation for the perimeter of a circle. This is a circle, right? And then, to get the area of a ring, right, it's just pi d, perimeter of your circle, multiplied by the thickness of this tank. So it's pi dt. So pi a becomes sigma times pi dt. Okay? And then in the same way, your force comes from your pressure. And pressure is equal to F over A. Therefore, F equals PA. So P is the pressure. And then A is the projected area of that pressure, which is, actually, let's choose green. Para mas obvious. And then the projected area of your pressure is the circle. Okay? So that's again an area of a circle. That's just pi over 4 d squared. So P times pi over 4 d squared. Okay? And now we can sub in our values. So this sigma is represented by this. That's the maximum stress your material can experience. Okay? So what is this? So that sigma is equal to 1 half. Let's simplify first to make things easier. Pi cancels out, and then P of D cancels out. So we're left with sigma T equals P times D over 4. Okay? So sigma T, that's 8,000 psi. Our thickness is in inches, 5 over 16. Okay? Equals P, which is what we're looking for. Our diameter is in feet, our stress is in inches, so I need to convert feet to inches, okay? So P times, that is 4 feet. Conversion, 1 feet, 1 foot equals 12 inches, right? So 1 foot equals 12 inches. Over 4, feet will cancel out, we're left with inches. So please solve. What is P? Correct, Beatrice? And Rishaline, Pascual, and Trias. So, Ricafort and Gutierrez. Okay. That is 208.33, and then unit is the same here because that is where we base our units. PSI. Now there's an easier way to solve for this. If you can figure out what is the equivalent of this stress, okay, because the stress again is experienced by this area. What's the equivalent to that of a cylinder? Is that tangential or longitudinal stress? Can anybody tell me? Is this tangential or longitudinal stress? Sige, sagot kayo lang. Remember how the equations were derived. Very good, Sierra. It's longitudinal. Why? Okay, let me show you the difference between longitudinal and tangential, okay? So for a cylinder, remember how I derived the equation for a cylinder, right? We took a portion, or we took half, okay? And then I said, this is the area experiencing stress for tangential. Okay, so for tangential, this is where the stress is being experienced. And the longitudinal, okay, so we again get a cylinder. Okay. I'm gonna cut it in half. This is that area. Okay? So this is tangential, this is longitudinal. Let's look at our derivation. As you can see, tangential along the sides, longitudinal along the perimeter. So the naming is a bit confusing. Okay? So the reason why this is tangential stress, because as you can see, these forces are tangent to your vessel. So this is your vessel, your forces are tangent. So tangent is like this, right? And then this is longitudinal because these stresses, if you look at it from the front, are along the length, follows the direction of the length of your vessel. Right? Okay? That's the difference. So now you know, again, tangential, longitudinal. So we can solve this just using longitudinal stress, sigma L equals PD over 40. Sigma L is 8,000 equals P, which is what we want. D is 12, 4 feet multiplied by 12 to convert to inches. Then over 4, thickness is 5 over 16. You should get P equals 208.33 PSI. Okay? As you can see, the sphere doesn't have any tangential stress. It only experiences longitudinal stress. Okay? Any questions for number 2? Okay, great. Let's move on to the next question. Number 3. A vertical cylindrical gasoline storage tank is 30 meters in diameter and is filled to a depth of 15 meters with gasoline whose specific gravity is 0.74. If the yield point of the shell plating is 250 MPa and a safety factor of 2.5 is adequate, calculate the required wall thickness at the bottom of the tank. Okay. So basically, we have storage tank filled with gasoline. So we want to know the required thickness at the bottom of the tank given this yield point of 250 MPa and factor of safety of 2.5. So we're looking for thickness. First step, write the given. 30 meters in diameter for the storage tank, so that's D. 30 meters. By the way, let's use capital D since that is how we did it in our equation. Okay. So D is 30 meters. Filled to a depth of 15 meters. Let's call that H for depth or height. Okay. So H, 15 meters. Specific gravity is 0.74. So that's GS. Okay. Specific gravity. That's the symbol for specific gravity, G sub S, in case you haven't encountered that yet. And then yield point of the shell plating is 250. So yield point should have been discussed to you in mechanics as well. But yield point is the point where your material starts to deform and it doesn't return to its original shape. So meaning it's the point where the deformation starts becoming permanent. And we want to avoid that. We want to avoid permanent deformation. So the yield point then effectively becomes our maximum stress, allowable. Okay, so this is your maximum allowable stress is 250 MPa. Let's call that sigma max 250 MPa. Okay. Factor of safety 2.5, that's Fs. 2.5, what else? That's it. We're looking for T. Now let's try to illustrate what's happening. I'm going to draw a front view. So you have this cylindrical tank, right? It's filled with gasoline. Let's use gray for gasoline, okay? Even though it's black. Okay? And this is that height, H. That's your 15 meters, okay? And we want to know the required thickness here at the bottom of the tank. Now, the reason why the bottom of the tank is important is because for liquids, pressure gets higher the deeper it gets. So meaning here at the bottom of the tank, pressure will be maximum. Okay, so that's why thickness at the bottom is important. Okay, so that's the same reason why whenever, if you've experienced diving, or if you watch videos, the deeper you go, the more dangerous it is because the pressure increases and it could burst your eardrums because again, pressure is too high. And to get the equation for that pressure due to your liquid, okay, so let's specify it. Okay, so at the bottom, okay, pressure equals gamma H. What's gamma? Gamma is the specific weight or unit weight of your liquid. So specific weight of your gasoline. And H is the height of your gasoline. So there. So that's how we get the equation for P. Okay? And after getting the equation for P, the problem is, how do I get the unit weight of gasoline? It's not given, right? We're not allowed to search the internet. But you're given specific gravity. So specific gravity actually equals, okay, unit weight of your material over unit weight of water. Okay? And unit weight of water, I'll place it here. Unit weight of water is 9810 Newton per meter cube. Okay? So therefore, gamma is GS times gamma water. Okay? So that's our equation for P. So P is just GS gamma water times H. Okay? So now we're going to use that in our restriction, the sigma max. And once again, whenever we have a restriction between longitudinal and tangential, we should use tangential because that's the critical stress. So use critical stress, again, because that's the most likely to fail or cause failure. So that's sigma T. And sigma T is PD over 2P. Sigma T is 250. So 250 equals, pressure is this, gamma H, and gamma is GS times sigma W, unit weight of water, times H. Okay? And take note of the units. Okay? This is meter cube. Our stress is MPa, that's Newton per millimeter squared. Okay? All of these are in meters. So I need to convert that pressure into millimeters. Okay, that's why I'm gonna multiply this. Okay, conversion factor 1 meter. Yeah, 1 meter is to 1000 millimeters. Let me specify. The unit of this is Newton per millimeter cube. Convert that Newton per meter cube. Convert that to millimeter. So 1 meter is 1000 millimeters, right? And then cube, because this is meter cube. Okay? And then diameter 30 meters. So times 30. Once again, this is meters. I need to convert it to millimeters. So times 1000. Ah, wait, H pa pala. This is only gamma. Then H, height is 15 meters. So 15 meters, again, convert to millimeters times 1000. Let me just move it. Okay? Dito. Okay. And then that's only the pressure multiplied by diameter, which is 30 meters. Again, convert to millimeters because our stress is in millimeters. Okay, then over 2t. And then from this, let's plug in our values. Okay, stress. Okay, okay. Again, P pressure, G is sigma W times H times D. That's your P, this is your D, over 2T. Okay, this is 250 equals, GS is 0.74. Sigma W again is 9810. Okay, conversion factor for the unit weight, millimeter, meter to millimeter, and then multiplied by H, which is 15 meters, convert to millimeters, multiplied by diameter D, which is 30 meters, convert to millimeters. Okay, so now that we have that, we can solve for T. Please solve. What's T? No. Remember, this is cube. Correct. Sierra and Beatriz. Gutierrez and Pascual, it's 6.53. 2 points ka na eh. Pangiling. Okay, so correct, Andrea. Pangi. So the answer is 6.53. And remember, we converted everything to Newton and millimeter. So the unit is millimeter. And that is our required thickness. Okay. So that's number 3. Any questions for number 3? Please answer in the chat. Okay, great. Since we don't have any questions, let's move on to the next question, number 4. Okay, so number 4 is a bit complicated, I believe. There are 2 ways to answer this. So a water tank 22 feet in diameter is made from steel plates that are half an inch thick. Find the maximum height to which the tank may be filled if the circumferential stress is limited to 6,000 psi. The specific weight of water is 62.4 pounds per cubic feet. So specific weight, again, same as unit weight, In metric system, that's 9,810 Newton per meter cube. For English system, it's 62.4 pound per cubic feet. Okay. So again, we're given maximum stress, circumferential stress to be exact. We're looking for maximum height to which the tank may be filled. We're looking for H. Okay. So again, first step, write our given. Okay. So first, 22 feet in diameter. So D, 22 feet. Steel plates, that's the thickness of your vessel, so half an inch. Circumferential stress is the same as tangential stress, 6,000 psi. So sigma T, 6,000 psi. Specific weight, that's your unit weight, 62.4 pounds per cubic feet. Right. So the first method here is assuming pressure distribution is uniform. Okay. So we're making an assumption. So this is the first method to solve. Okay, so we have water tank with the diameter. So that's a cylindrical tank. Okay, so let's draw a cylindrical tank. Mm-hmm. Okay. And then okay. Mm-hmm. Okay, I need. Okay, there. All right. So this is a cross section of our cylinder, right? So what happens here is, since we're assuming pressure distribution is uniform, so instead of having maximum pressure here at the bottom, the pressure is just the same everywhere else. So meaning, we have this. We're going to have a projected area for our pressure. Okay? So RP is still equal to gamma H, right? Gamma is given. H is what we're looking for. Okay? Then we're going to use this in our equation to solve for maximum height. Okay. So as usual, we already know whenever we're solving for a maximum stress, we're going to use the critical stress, which is tangential. Also, that is the stress that's given. So tangential is PD over 2T. Tangential is 6,000 psi equals P. Again, P is gamma H. Our gamma is 62.4 pounds per cubic feet. Okay. Now I need to convert that to cubic inches or to inches because again, our stress is in PSI. So 62.4 times, this is pounds per cubic feet. Converted to inches. So 1 foot equals 12 inches. Okay, right. Feet cancels out. This is cube, so this should also be cube. Okay, that's your gamma. Next, H. Okay, so that's your H. Those times D. D is 22 feet, and once again, convert 22 feet to inches. So 22 times 12 over 2. Our thickness is half an inch, so that's times 0.5 or 1/2. So from this, we can solve for H. Please solve. What's H? Hmm? In inches. Inches tayo. So correct, Edwin and Miguela. So Muni and Mira. Hmm? Late and Rosie. Right. Yes. 629 inches. So 629.37 inches, or convert that to feet. So divided by 12, that's 52.45 feet. Okay, so that's our answer for H, assuming pressure distribution is uniform. Okay, but we know pressure is not uniform. It gets greater at the end. So our diagram is not just a straight rectangle. Okay, we won't use a projected area. So instead, we're gonna solve for the actual height allowed. So we're not gonna assume anything. We're gonna use the actual pressure distribution. Okay, I'm gonna get this. Okay, so now the pressure distribution doesn't look like this. Okay, it's gonna look like, so it's zero at the top portion of your liquid because obviously there's no pressure at the surface area. And then it gets maximum at the bottom. So from zero and then maximum here. Okay, right. This represents your pressure distribution diagram. So this is the actual pressure distribution, not this where it's just a straight line, okay? Incorrect. So this is our actual, okay? And then, so now pressure is not gamma H, okay? Or rather, you can't use this equation anymore. We need to analyze what's happening to our cylinder because the equations that we used earlier were based on uniform pressure. Okay, so that's why we can still use this because we assumed uniform pressure. Since that's not the case anymore, we need to derive a new equation. Okay, so to do that, we'll look at our drawing. So recall, the way that we derive is we looked at the pressure, and that pressure creates a force. So same thing here. This pressure, illustrated by this pressure diagram, creates a force F. So that's still applicable, okay? So we still have a force F, total force F acting on our vessel. And then this force F is being resisted by your pressure, by your vessel itself. Because of that, it's going to experience stress. Okay? And then that stress creates a force resisting F. Let's use violet. And it's going to resist along the sides because your force is here. So therefore, the area that's perpendicular to that is the one resisting. So it's these two. So it's going to resist like so. Okay? So we'll call that P again, because again, that force is actually tangential. Okay? And then how do we get the equation for force F? F is the volume, or F equals volume of your pressure diagram. If before, force is just stress, pressure times perpendicular area, now the equation, since again we don't have uniform pressure, is the volume of your pressure diagram. Okay? Great. So let's compute. F equals, this is a triangular prism, right? Can anybody give me the equation for the volume of a triangular prism? from your math class. Volume of a triangular prism, or even just by looking at the figure. What's the volume of this? Very good, Trinity. It's 1/2 base times height times length. Okay, so 1/2 base times height times length or width. Okay, in this case, 1/2 base, our base is this, and that's actually equal to this length is equal to gamma h. Okay, because that's the bottom pressure, bottom value of your pressure. And we know from the previous, at the bottom pressure is gamma h. Same thing here, at the bottom, this is gamma h. Okay, what else? So base is gamma h, height is still height, h, and then width is this. And that is actually, this width is the diameter of your storage for your vessel. 1/2 h times 3. Okay, so let's compute. 1/2 gamma h, again gamma is 62.4. H times h squared. And then d is 22. Now I'm not converting it to inch yet because we don't need to yet. We're not comparing anything. These are all still feet, and h is in feet. Okay. So what's 1/2 times 62.4 times 22? Correct, Audrey and Trinity. So Davao, Manrique. 686.4. Don't forget we have a variable here, h squared. So this is our equation for force F. So we're gonna use that and compare it to T to create our equation. Now, how do you do that? Okay, so recall from your MEC30 class, right? We have ourselves a system of non-concurrent forces. To see it clearer, I'm gonna draw side view. Okay, so let's say, let's make everything smaller para magkasya. Oops. Okay. Okay, so side view. Side view, right? This is your vessel. It's gonna be filled with water up to here. Okay. And then this water has a pressure distribution diagram that is forming a triangle. Okay. So it's 0 at the top because there's no pressure at the surface. Then it's maximum here at the bottom. Okay. And then remember, whenever we have a pressure diagram, so remember from your MEC30, when we have a load diagram, to get the resultant is just the area of your load diagram. Now, if we have a pressure diagram, the resultant is the volume. And recall where the position of those resultants are placed. It's at the centroid of your figure. Okay, so therefore this F will be at the centroid of this prism, which is triangular. And we know the centroid of a triangle is 1/3 from the base, a 1/3 base from the higher end. This is the higher end. So this is where your force F will be. Okay, force F. And then this is 1/3 base. 1/3. This is your base, which is actually equal to h. So 1/3 h instead. Okay. Now how about this t? Let's choose a different color. 1/3 h. Now what about this t? Where will that act? So that's actually right at the center of this area. Okay. Meaning it's gonna be somewhere here. There's two of them, so this total is 2t. Okay? And as I mentioned earlier, we have a set of non-concurrent force systems. So this is, since this is at the middle, that's just half of your h. Okay? So whenever we have a non-concurrent force system, one way to solve for the missing variables is to use your equilibrium equations, your summation of forces, or your summation of moment. For this case, we're gonna use summation of moment. Okay, so let's call this point A. So let's do summation of moment at A to create a relationship between your resistance P and your force F. So summation of moment at A equals 0, right? Let's start with 2t. 2t rotate about A, that's clockwise, so positive 2t times distance, which is 1/2 h. Okay, next, rotate F about A, that's counterclockwise, so negative F, and distance from A is again 1/3 h. Equate that to 0. Then you'll see h cancels out. So we have 2t times 1/2, that's t, equals 1/3 f. Now what will I do with this? Now I have an equation for t in terms of f. I can actually use that in the next set of equations. Okay? So again, this t comes from the stress within your material. So the equation of that would be sigma A. So sigma A, where A is this, right? And the area of that is just the thickness of my material. So this is T times height h. So that's why this is sigma T times h equals 1/3. And then what's F? F is this. 686.4 h squared. As you can see, h cancels out. Sub in our values. Sigma, that's the stress being experienced by your material, which is given to be 6,000 psi, or allowed to be 6,000 psi. So 6,000 times thickness, since h cancels out, thickness is 1/2 inch. So 6,000 times 1/2 equals 1/3, 686.4. Okay, then h. However, recall the unit of this are all in feet, right? So this unit is actually pound per foot. My stress is in inches, so now I need to convert this into inches. So pounds to inch, the unit of this is pound per foot. So, wait, busog ko lang. Okay. Again, this equation is pound per foot. Convert to inches. So 1 foot equals 12 inches. And that's it. From this, we can solve for h. Please solve. What's the answer? Inches. The answer is in inches. Yan. Okay. So correct, Krishaline and Julia. So Solomon and Trias. Okay. So our answer was in inches. So H equals 1888.11 inches, or it's more convenient for feet for height. So 157.34 feet. As you can see, the actual allowable height is very much larger than from computing from assumption. But this is more conservative. Conservative meaning it gives a lot of leeway for excess stress. Okay, so that's why this method of assumption is acceptable as well. Okay, so that's number 3 or 4. Any questions for number 4? Please answer in the chat. Okay, now let's answer the next question. Number 5. Second to the last number for thin walled pressure vessels. The strength of longitudinal joint in the figure is 33 kips per feet, whereas the girth is 16 kips per feet. Calculate the maximum diameter of the cylinder tank if the internal pressure is 150 psi. So basically, we're looking for maximum diameter given the strength. And again, strength is the maximum allowable stress. So 33 kips and 16 kips given internal pressure 150. So there's an easy way to solve for this if you understand the difference between longitudinal stress and circumferential stress. Okay. Let me just copy that image because I don't want to draw anymore. Okay. That's the drawing. Let's have our given. Longitudinal joint 33 kips per feet. That's not equal to longitudinal stress, okay? Read carefully. Strength in longitudinal joint. That means strength along this joint. So can anybody tell me, is that longitudinal stress or tangential stress? Yeah, very good. It's tangential. Very good, Jade and Edwin. So Mira and Romilo. Tangential. So this is actually sigma t, right? 33 kips per feet. And then we have strength for the girth. So strength for this area, right? If this is already tangential, then obviously this is now your longitudinal, which makes sense because as I mentioned earlier, yeah, tangential is along here, longitudinal is along here. Okay, so longitudinal 16 kips per feet. Okay, so now that we know this, the solution will be easy. We'll just check for the diameter of each. Okay, so maximum diameter. Can anybody tell me which of the two is critical, tangential or longitudinal stress? Which should we test? Tangential or longitudinal? Which should we use? Can I ignore one of them? Very good, Janelle and Miguel, it's tangential. As I've said, tangential is always the critical stress. So Flores and Mooney. So all I need is sigma t. So sigma t is equal to PD over, yan. Okay. Now, by the way, the given here is kips per feet. However, our stress should only be kips. So this given is actually stress per thickness. Stress per thickness. Okay, that's why there's a per feet here. So I'm gonna divide both sides by t. We get stress per thickness equals PD over 2. And stress per thickness is 33 kips. So 33, right? What's our pressure? 150 psi. This is just pounds, so I need to convert kips to pounds. That's just times 1,000. So times 1,000. Again, this is a conversion from kips to pounds. Equals PD, that's 150. D is what we're looking for. Over 2. That's over 2. Wala na palang thickness. So please compute what's D. Oh wait, let's. Sorry. My bad. Di pa tayo tapos. Wait lang. Okay. Units. 33 kips per feet. PSI. So I need to convert this as well to inches. Okay, so 33 kips per feet times. Okay, so 1 kip is 1,000 pounds. And then times, convert feet into inches. 1 foot is equal to 12 inches. Equals 150. That's PSI already. This is what we're looking for. D over 2. Yeah. Solve again. What's D? Correct. 36.67 inches or 3.06 feet. Okay. Correct. VMA. Sierra, 2 points ka na. Then, Pamitan. Philip. So, Pamitan and Vergara. Okay. 36.67 inches. Or again, you can convert to feet or 3.06 feet. So that's the answer. Now, if you try to solve, okay, I'm going to give you the answer if you try to solve for using longitudinal stress. The answer for D that you'll get is 35.56 inches or 2.96 feet. Now, as you can see, this is greater, 3.06 feet versus 2.96 feet. Now, we're going to choose, when it comes to dimension, we're going to choose the larger one. So it's the opposite for force. When we're given choices for force, we're going to choose the least amount. For dimensions, that's different. We're going to choose the higher amount. Okay? So calculate the maximum diameter is 3.06 feet or 36.67 inch. Now, if you're wondering why can't I use this? Because this is the minimum required diameter for this vessel to avoid failure for tangential stress. Okay, anything less than this will create failure. That's why 2.96 creates failure. Okay, that's why this is our answer. Okay, it's number 5. Do you understand? Do you have any questions? Please answer in the chat. Okay, great. The next problem, number 6, I'll answer next meeting because the solution of this requires a bit of an analysis and we only have 10 minutes left, so I don't want to rush through that. Okay, now with that said, that ends the lecture for today for thin wall pressure vessel. Now a few announcements before you go. On Saturday, holiday, so no classes on Saturday. Therefore, on Tuesday, we will have our quiz number 1. Okay, coverage for quiz number 1 is up to shear and bearing stress only. Okay, understand, shear and bearing, up to shear and bearing stress only. So everything up to that topic. That means thin wall pressure vessels is not included in your quiz number 1. Okay? So Tuesday, 3 to 4:30 p.m. Open camera, join the Zoom meeting. No video, no score. Remember that. Deadline for answering your quiz, soft deadline is at 4:30 p.m. Deadline for submitting your solution is 11:59 p.m. So remember, every time we have a quiz and seat work, there's always a submission of solution. Okay? So 11:59 p.m. Once again, coverage up until shearing stress and bearing stress. Okay? Do you have any questions? Clarifications? Issues? All right. And by the way, next deadline of your seat work is still this Saturday. For those who haven't answered, please answer until Saturday. You don't have to message me about it. Don't have to send an excuse letter. Just answer it within the week. Okay? I only need excuse letters or explanation letters for quizzes. And then try to answer your Coursera activity week 1 and 2 as well, because the deadline for that is next week, Saturday. Okay? So those are my announcements and reminders. Wala nang tanong, wala nang hahabol. Alright, so since you don't have any more questions, sorry, my bad. We don't have Coursera, my bad. Sorry, I'm confusing you with my other class because I'm also teaching MEC30. We have Coursera there. Yeah. Sorry, my bad. We don't have Coursera. Scratch that. So anyway, so seat work lang. Remember your seat work. And quiz next week. Okay, that's it. Since you don't have any more questions, you may go. Enjoy your holiday. Goodbye, class.